Alrighty, today in this video, we're going to be talking about 5.2 properties of functions. So a couple of things. We're going to start off with symmetry. There's three types of symmetries. There's y-axis, x-axis, and the origin. All right, so symmetry. We have first the y-axis. It is symmetrical if you plug in the value of negative x and you pop out with the original function. And that's how you would know if something is symmetrical. It is also called an even function. All right. Then we have the origin, and it is symmetric. So it is symmetrical around the origin if I plug in negative x, and I pop out with everything is negative now. Every sign changed. Sorry, let me rephrase that. Every sign changed. Not that it all became negative, but the signs all changed. That would resemble a origin symmetry, and it's also called an odd function. When we are looking at symmetry around the x-axis, that's an E. You want to replace the y with a negative y and get, sorry, let's erase this. So replace y with the negative y and get the original function. It's neither even nor odd here. I will say to kind of help you out when you're doing the work, you can start off by checking if it is the y-axis and the x-axis pretty easily. And then if not, then you just replace the y with negative y to see if it's at least x-axis. All right. That's pretty much it when it comes to symmetry and even odd functions. It's got some examples graphically for you. And then we go into increasing, decreasing. So something is increasing if from left to right, the function is going up. It is decreasing if from left to right, the function is going down. It is a constant if from left to right, the function stays the same. The big thing about this is that's pretty straightforward, but the answer is the x-axis. Meaning if I'm saying it's increasing from 3 to 10, it's because I'm looking at the x-axis and it's increasing from 3 to 10. Like the function itself is increasing, but I'm taking the answers from the x-axis. So that's going to be the part that usually gets a lot of kids. They just forget how to answer it. All right, and then the next one is extremis. So we have local extremis. So you have local min And basically, it is when you change from decreasing to increasing. So something like this. So if I have a graph that's going like this, I'm decreasing and then I'm increasing. So that right there would be a local min. A local max is when you change from increasing to decreasing. So again, that's something like this. So I'm increasing, then I'm decreasing. So that'd be a local max. And that's basically what the book is trying to tell you there. And then we just have a new way of saying average rates of change, also known as AROC. It is now written as f of b minus f of a over b minus a. And I will say, if you're going further in your math career, like calculus and things like that, you're going to pretty much see this formula more than you'll see something like the change in y over the change in x, or y2 minus y1 over x2 minus x1, or rise over run. All these mean the same thing, but you will see now this one more than anything. It's actually our preparedness for what we call a secant line, which is just telling me what the average rate of change is between 2 points. On any type of graph, no longer linear. And then eventually, when you go into calculus, you'll learn what a tangent line is. And a tangent line basically is finding the average rate of change at any given point in time. And then that's a whole different topic for a different class, but definitely something that you'll be going towards if that is what you are choosing to do. All right, so let's jump into some exercises. I'm going to be on page 337 today. And I'm going to look at number 1. All right, so in the directions, it says determine if each of the following relation is a function. And then if so, determine whether it's even, odd, or neither. Also determine if it has a y-axis symmetry, x-axis symmetry, origin of symmetry, or none of the above, and then sketch the graph of the relation. All right, so when looking at number 1 here, I'm given the absolute value of x plus 3. So the first thing I need to determine is if it's an even or odd function, or actually determine if this is a function at all. And you can tell that this is an absolute value function, so it is a function. But determine if this is a even or odd, I'm just going to replace the negative x in there and see what I get. I know all absolute values will end up just being a positive anyways, so I can see I got the original function. So that tells me it's an even function, but it also now tells me that it is symmetrical around the y-axis. So we know that even and y-axis are the same, odd and origin are the same. So if it's even and over the y-axis. All right, and then I want you to sketch the graph. So kind of going off last video, I know that the parent function looks like this. So the plus 3 tells me to go up 3. So my graph looks roughly something like this. All right, let's look at number 2. I have g of x equals x cubed. Again, I'm going to plug in negative x, see if it's even or odd. I know anything raised to an odd exponent will stay odd. So I can see that all the signs change. So therefore, it is an odd function. And if it's odd, I also know it's reflective around the origin. So this right here saves a lot of time when these events happen. After that, I'm just going to graph it. And this is the parent function in itself. So it looks just like this. All right, let's look at number 4. Number 4 says w of x equals the cube root of x. So again, I'm going to check to see if it is even or odd. I know that a odd index of a radical is just going to remain odd, not odd, sorry, negative. So therefore, I know then that this will be a odd function. And if I know it's an odd, then I know it's an origin. And this right here is just the parent function, and this is what it looks like there. And you can kind of tell graphically that the origin is reflecting these two. Over here, the y-axis is reflecting it, and again, right here, the origin is reflecting it. And when you're told the origin, if you didn't know as well, this is the origin. Well, if I was a better drawer, but there'll be the y equals x. That's the origin. All right, let's see. So let's look at number 8. Number 8 says f of x equals x minus 1 squared. So again, I'm going to plug in negative x minus 1 squared. And I can see that it affects the negative, but not this one. And if I would happen to have to fold this out, I would get a negative 2x in the middle, but in the middle of the second one, I'd actually get positive 2x. So the function would not be exactly the same either, and it wouldn't have changed every sign either. So this is neither even or odd. So it's neither even or odd. And then the only way to really determine if this is reflective over the x-axis is if I then replace this as a negative y. So if I was to say, hey, this is negative y equals x minus 1 squared, to solve for y, I would then multiply by negative. So that would make this a negative x minus 1 squared, but I want the original function. This will change all of the function. So therefore, this is neither even, or neither even or odd, and neither symmetrical to anything. So again, for this to bend the x-axis, sorry, not the y-axis, if I made this a negative, resolved for y, I should get the original problem back, and I won't. And I can kind of see when I graph this, this right here is a horizontal shift to the right. So my quadratic will now be here. And since I shifted it, it's no longer symmetrical around the y-axis or the x-axis or the origin. Right? So when you start moving, shifting things, your symmetry starts going out the window. Let's look at number 11. Number 11 says g of x equals x squared over 5 minus 5. This time I'm going to plug in negative x, and so I'd get negative x squared over 5 minus 5. Negative squared will just go back to a positive, so I can see I'm getting the original function back. So that's going to be even, and if it's even, it's symmetrical around the y-axis. And I can kind of graph this as well. This is going to be a quadratic that has a vertical shift of 1/5, and it went down 5. So in a rough sketch, it's probably going to be a big guy right here. So I get a function like this. Alrighty. Okay, so that's good for that section. Then the next section says for each of the following functions, find the open intervals where the function's increasing, decreasing. Best thing to do here is actually to graph it, and then you can just look at your graph. I'm going to try to teach it without it. So knowing that the graph is now shifted to the left 3, but I still have a quadratic here and here. I just have to determine when the function's increasing or decreasing. So when I do this, I like to look at the graph from left to right, and I can see I'm going down first. So I'm going to say my decreasing intervals are going to be from negative infinity, because I'm going from the x-axis all the way to negative 3. So at this point, my function is no longer going down, it's changing directions at negative 3, and then from all the way to infinity, I can see the function's now increasing. At no spot did it actually remain constant. Constant would be a flat line. All right, so you can graph it and then visually look at it as well. Let's look at another one. Let's look at number 21. This is f of x equals -2. A constant graph, I don't know if we've gone over many of these, just makes a horizontal line. So that means it did not increase nor decrease. It remained constant the entire time. So from -infinity to infinity. And the all real number symbol, I do not believe it does work here. In the past, in other books, they want it as intervals, but you can say all real numbers here as well. All righty, so let's look at another set. So let's look at number 27. In this section, it says, use the graph of each of the following functions to determine the location and types of local extremas. And then part B, the values of the local extremas. So that's kind of the same thing. So I'm going to locate it, and I see the first extrema would be at, and it's going, -1, 0. And because it goes from decreasing to increasing, this will be a local min. And then I see another extrema at 2, 3. And that right there would be a local max. So I found the values and then just label them from there. Yep. So there you go. Then you might see on the homework, you might see something. There's a value. Oh, that's not a value. A value at -1 is 0. And you might see the value at 2 is 3. So you might see it written this way as well. All right, let's do another one to make sure we got that down. So looking at number 28, again, I can see I have a local extrema at -2, -3. And that right there would be a local minimum. And I have another extrema at 0, 1. That would be a local max because, again, it's changing from increasing to decreasing. And then I see I have another one at 1, -2. And that looks to be like a local minimum because, again, it went from decreasing to increasing. And that's all you have to be able to do. Let's see. So the only other type of questions I saw were questions like number 49. It says use each graph given of the function and the marked locations on the x-axis as the endpoints to determine intervals over which the average rate of change of the function is either positive, negative, or 0. So you don't actually have to calculate anything. You just have to determine what's the intervals at which they are increasing at. So I didn't actually see any in your homework where you actually had to calculate the average rate of change. So got lucky there. If that changes, though, let me know. All right, so again, I'm going to read the graph from left to right so I can see the function is, okay, I guess using these points, which one would give you an average rate of change in the function? All right, so looking at A to B, hold on, make sure I'm answering this question right. Oh, I see. Okay, I got you. This is broken down differently. So A, what are all the intervals in which you would get a positive slope? So that would be the interval from A to B because it went up. I would not do A to C because that remained the same, and I would not do A to D because that remained the same. So then B was what's all the ones that give you a negative. So I would say B to C would give you a negative, and B to D would give you a negative. And then for the last one, a constant, I would then at this point say A to C and A to D would give you a constant rate of change. Now let's look at number 50 just real quick. So again, A being positive, that would be A to B. And then that would be it. And then B would be B to C. And that would be it. And then C would just be A to C as a constant. So just kind of looking at it and seeing if you put the 2 points together, what kind of slope would it bring? And that's pretty much all I got in this one as well.